What you're looking at right here is oxy-fuel cutting. You'll find this process in pretty much any fabrication shop or field site. It's just a fundamental way to sever carbon steel. Now, a lot of people think this is a melting process, but it's not. What's really happening is a very controlled, high-temperature chemical reaction. We're essentially using a jet of pure oxygen to rapidly oxidize the iron in a very precise line. So let's break down the equipment and the physics that make this whole thing possible.
And this is the goal. This is what a high-quality cut looks like, and every feature you see here is proof of a process that was perfectly under control. Take a look at those drag lines. See how they're almost perfectly vertical? And notice that sharp, square top edge with no melting or rollover. Getting a cut this clean tells you that the travel speed, the torch height, the gas pressures, everything was dialed in just right. So to get this result every single time, we've got to understand how each piece of the system really works. Okay, so this whole process hinges on two gases. First, you've got your oxidizer, oxygen. Now, here's the thing about oxygen. It's not flammable on its own, but it's absolutely essential for combustion. It supports the preheat flame, and more importantly, it's the key ingredient for that high-speed oxidation that actually does the cutting. Then you have the fuel, acetylene. It's a fantastic, high-energy fuel gas, but it's also a little bit touchy. From an engineering standpoint, its most critical property is its instability. You see, in its pure form, under even pretty low pressure, it can become self-explosive. And that one single fact dictates the entire design of how we store and deliver. So that leads to a big engineering problem. How do you safely store a gas that wants to decompose all on its own? Well, the solution is pretty clever. You never store it as a free gas. Instead, an acetylene cylinder is packed with a porous, solid material, kind of like a hard sponge. Then, that material is completely saturated with liquid acetone. The reason? Acetone is incredibly soluble in acetone. So the gas dissolves and is held safely in that acetone, spread all throughout the porous filler. This brilliant design prevents any large pockets of pure, free acetylene from ever forming, which lets us store it safely at pressures up to 250 psi. And here are the hard numbers on that danger, straight from the source material. At just under 30 psi, free acetylene can decompose explosively without any spark or ignition source at all. So to give a massive safety factor and stay far, far away from that danger zone, the industry has a strict, non-negotiable rule. The absolute maximum working pressure for acetylene is 15 psi. That's not a guideline. It's a critical safety boundary that you have to respect on every single setup. So how do we get from that high pressure inside the cylinder down to a stable, controlled working pressure? That's the job of this device right here, a two-stage regulator. This is basically the control center for your gas delivery. The high pressure gauge, that's your fuel gauge. It shows you how much gas is left in the bottle. The low pressure gauge, that's the one the operator sets. That's how you dial in the precise pressure you need at the torch tip while making absolutely sure you stay safely below that 15 psi limit for the acetylene. Its entire job is to provide precise, rock-steady pressure. The cutting process itself, right at the torch tip, is really a two-step dance. Step one is all about preheating. You use a flame from a mix of oxygen and acetylene to heat a small spot of the steel up to its kindling temperature. We're talking about 1600 degrees Fahrenheit, which you'll see as a bright cherry red glow. Now, the only purpose of this flame is to get the iron hot enough so that it's ready to react with pure oxygen. I want to be really clear here. We are not melting the metal. As soon as that spot hits kindling temperature, the operator hits the cutting oxygen lever. That's stage two. This unleashes a high-velocity jet of pure oxygen right out of the center of the torch tip. This is what does the actual cutting. It kicks off a rapid exothermic oxidation of the iron, and that chemical reaction creates a ton of its own heat, which helps sustain the cut. At the same time, the force of that oxygen stream literally blows all the molten iron oxide, what we call slag, out of the cut, creating the opening. You know, the great thing is, the finished cut gives you direct feedback on your technique. A proper inspection looks for four main things. You want drag lines that are uniform and nearly vertical. The cut surface itself should be smooth and flat. That top edge needs to be sharp and square with no rounding. And finally, any slag on the bottom should be minimal and super easy to just chip away. If you see any problems with these, it's a dead giveaway that something was off. Your travel speed, your torch height, or your gas pressures. And this comparison right here is a perfect example. The cut on the left, that's what you want. It meets all the quality checks. See that sharp, square edge? Now look at the cut on the right. See how the top edge is all melted and rounded over? That is a classic sign of way too much preheat. Either the preheat flame was too big or the operator was moving way too slowly. They were basically just melting the top surface instead of letting the oxygen jet do its job. Okay, We have to talk about a critical failure mode, a flashback. This is when the flame actually burns backward, up from the tip, inside the torch. It's often paired with a really distinct hissing or squealing sound. This is an extremely dangerous situation. The immediate emergency procedure is to shut off the oxygen valve on the torch first, and then shut off the acetylene valve. Oxygen first, and you do not, under any circumstances, relight that torch until you have found and fixed the root cause, whether it's a clogged tip, wrong pressures, or damaged gear.
And here's another fundamental safety check: the color coding on compressed gas cylinders. This system is a simple visual way to prevent you from hooking up the wrong gas to the wrong equipment. Now, the label on the cylinder is always the final definitive word, but these colors are your critical first line of defense. The standard practice in the US is green for oxygen cylinders and yellow for acetylene. Knowing these codes is an absolute basic requirement for anyone handling this equipment.
So, we've walked through all the mechanics, but this brings up a deeper metallurgical question. That preheat flame, its chemistry changes depending on your oxygen-to-fuel ratio. You can have a carburizing flame, a neutral flame, or an oxidizing flame. Each of those creates a different chemical atmosphere that's interacting with the hot steel right at the edge of the cut. So how does that affect the heat-affected zone? Does it change the carbon content, the hardness? What about the weldability of that cut surface later on? It's a reminder that this mechanical process has real chemical consequences, and for critical work, you have to understand them.